Okay, next example. The two equations here that make up this system that we're going to try to solve are xy equals 20 and x minus 2y equals negative 6. Can you see a good way of solving one of those equations for one of the variables? I think my choice would be to take the bottom equation and leave the x where it is, but add 2y to both sides. Then we get x equals negative 6 plus 2y, and we can substitute that in place of the x in the top equation, the one we haven't used yet. So when we do that, we get negative 6 plus 2y times y equals 20. So for now, forget that x even existed and work on solving this equation for y. If I multiply this out, I get negative 6y plus 2y squared equals 20. Now, that is a quadratic equation. It does have a y squared in it. So let's rearrange the equation to get everything on one side equal to 0 on the other side. So I'll leave the 2y squared minus 6y here, but put them in that order, and I will subtract the 20. So it's 2y squared minus 6y minus 20 equals 0. I notice all of those coefficients are even, so I might as well just go ahead and divide both sides by 2 and make things simpler. So then I get y squared minus 3y minus 10 equals 0. Okay, I think I can see how to factor that. That would factor into y minus 5 times y plus 2 equals 0. So then setting each factor individually equal to 0, I get y equals 5 or y equals negative 2. Now I can unforget that x existed. Remember, these are the y's, but we also have x's that have to go with them. So for each y, each number I got for y, I can plug it back in here and see what the x has to be that goes with it. So if y is 5, x would be negative 6 plus 2 times 5. That would be negative 6 plus 10, which would be 4. If y is negative 2, x would be negative 6 plus 2 times negative 2. That would be negative 6 plus negative 4, which would be negative 10. So our solutions, written as ordered pairs, x, y, we've got where x is 4 and y is 5, and we've got where x is negative 10 and y is negative 2. Here's what this looks like graphically. X times y equal to 20 is this two-part red curve, and x minus 2y equals negative 6 is this blue line. There are 2 points of intersection. One of them is 4, 5, where x is 4 and y is 5. 4 times 5 equals 20, and 4 minus 2 times 5 does equal negative 6. And the other point is negative 10, negative 2. Negative 10 times negative 2 does equal positive 20. And negative 10 minus 2 times negative 2 does equal negative 6. Next example, the system here has two equations. One of them is y equals x cubed minus 8x squared plus 3x plus 18. And the other one is y equals x squared minus 8x minus 3. Neither one of these is a linear equation, so we've got a nonlinear system, but we can still solve it. Let's make a substitution. Let's stick in what y is equal to in place of y, and then we get the equation x cubed minus 8x squared plus 3x plus 18 equals x squared minus 8x minus 3. How do we solve an equation like that? Well, let's start by getting everything on one side equal to 0 on the other side. So after subtracting x squared and adding 8x and adding 3, we get x cubed minus 9x squared plus 11x plus 21 equals 0. I remember we were solving equations like this a while back, like back in chapter 3. How many solutions would you expect an equation like this to have? This is a degree 3 polynomial, so it could have 3 equations. And if you remember about Descartes' rule of signs, I see 1, 2 sign changes. So there could be 2 positive real solutions, or possibly none. But there are 3 in all. 2 of them, possibly, are positive real numbers. The other one could be a negative real number. If any of those solutions are rational numbers, what are the possibilities? Remember how that worked? Look at the constant term and the leading coefficient, and the possible rational solutions are factors of that constant term over that leading coefficient, which here would be positive or negative 1, 3, 7, or 21, all over just 1. So since those are the possibilities, let's start trying numbers on that list until we get one that works. So if we try 3, if we do the synthetic division, set it up with 3 out here and 1, negative 9, 11, 21 here. Remember how that works? Bring down the 1, 3 times 1 is 3, negative 9 plus 3 is negative 6, 3 times negative 6 is negative 18, 11 plus negative 18 is negative 7, 3 times negative 7 is negative 21, 21 plus negative 21 is 0. We got a remainder of 0, which means that 3 is a solution. And not only that, but we know that we can take this and factor it into x minus 3, because that's what we were dividing by, times x squared minus 6x minus 7, because that's what we got as a quotient. So now we're looking for solutions to the equation x minus 3 times x squared minus 6x minus 7 equals 0. And I bet I can factor that x squared minus 6x minus 7 just by hand. I can break it up into x minus 7 times x plus 1. So now for the whole thing to equal 0, either x minus 3 equals 0, which means x equals 3, or x minus 7 equals 0, which means x equals 7, or x plus 1 equals 0, which means x equals negative 1. Now for each one of those x's, there's a y that goes with it that we can find by plugging that x into either one of these equations. I think the bottom one is easier to work with. So if x is 3, y should equal 3 squared minus 8 times 3 minus 3, and that works out to be negative 18. If x is 7, y must equal 7 squared minus 8 times 7 minus 3, which is negative 10. And if x is negative 1, that would give us y equal to negative 1 squared minus 8 times negative 1 minus 3, which works out to be 6. Now we could have plugged those x's into the top equation instead. We would have gotten the same things, but it would have been a little more complicated getting there. So our solutions, written as pairs of numbers with x and y together, are 3, negative 18, 7, negative 10, and negative 1, 6. And if you look at graphs of these two equations, the 3 points where the graphs intersect are 3, negative 18, 7, negative 10, and negative 1, 6. Okay, last example for this section. Here we're finding a break-even point when we have a cost equation and a revenue equation. So here we are told that the cost to produce X number of units of something is C equals 0.08X plus $50,000. So it costs 8 cents per unit for the raw materials. But we also have a fixed cost and overhead of $50,000 that we got to pay no matter how many units we produce. And our revenue equation is R equals 0.25x. So that's like we're selling these units for 25 cents each. So we're taking in 25 cents per unit. And we need to know how many units we have to sell to break even so that our revenue matches our cost. The amount of money we take in matches the amount of money we had to spend. So that's just a matter of setting these two equal to one another. If the R and the C are equal to one another, that means that 0.25x equals 0.08x plus 50,000. So we just have to solve that for x, subtract 0.08x from both sides, and we get 0.17x equals 50,000. Then divide both sides by 0.17, and we get x equals, well, this is what shows up on the calculator, 294,117.6471. But if x has to be a whole number of units, that means x has to be 294,118 units. So if we sell that many, we break even. If we sell more than that, then we start seeing a positive profit. So that's it for this section. Next time we'll come back and talk about another method of solving systems of equations, and we'll also talk about specifically for linear systems, how many solutions can we have and what are the different situations that can occur when you have two straight lines.